All right. Okay, so I thought we could finish the lecture from last time and keep talking about diffusion models. I also have another lecture on already on training latent variable models with discrete variables, but I thought since we didn't finish this and there was quite a bit of interest, maybe we can go through the remaining slides and really see the connections with ODEs, like efficient sampling strategies and all that good stuff. So as a reminder, we've seen that we can think of, there is this close connection between score-based models and denoising diffusion, DTPMs, denoising diffusion probabilistic models. The basic idea is that you can think of score-based models as basically trying to go from noise to data by essentially running these larger dynamics chains. And alternatively, we can think about a process that does something very similar from the perspective of a variational autoencoder. So there is a process that basically adds noise to the data, which you can think of it as an encoder. And all these transitions here, Q of xt given xt minus 1, this is just a Gaussian, which is centered at xt minus 1, and you just add a little bit of noise to get xt. And so at every step, you add a little bit of noise, and then eventually you add, after many steps, you've added so much noise to the data that all the structure is lost, and you're left with pure noise at the end of this chain. And as in a regular VAE, there is a decoder, which is a joint distribution over the same kind of random variables, and we parameterize it in the reverse direction. So we go from noise to clean data, and we have this sequence of decoders, and the decoders are basically this p theta of xt minus 1 given xt. And so given xt, you try to guess what is the value of xt minus 1. And these decoders are also, in the DDPM formulation, are also simple in the sense that they are Gaussian distributions, and the parameters of these Gaussian distributions are computed using neural networks, just like in a regular VA. And what we're seeing is that we can train these models the usual way, which is by optimizing an evidence lower bound, which essentially tries to minimize the KL divergence between the distribution defined by the decoder and the distribution defined by the encoder. It's kind of like trying to match those two joint distributions. And if you look at the ELBO objective, it looks like this. And it turns out that if you do a little bit of math, this objective ends up being exactly the denoising score matching objective. So in order to essentially, if you want to learn the best decoder, the best way of guessing xt minus 1 given xt, essentially what you have to do is you have to learn the score of the noise perturbed data density, and which we know can be done by solving a denoising problem. And so essentially optimizing the ELBO corresponds to learning a sequence of denoisers, the same as the noise conditional score models, essentially. And that's kind of like the main thing here, is that we can interpret the whole thing as a variational autoencoder. Minimizing the ELBO corresponds to essentially a sum of denoising score matching objectives, each one corresponding to a different noise level that we have in this chain. And so there is this very kind of like the resulting training and inference procedure in a denoising diffusion probabilistic model is very, very similar to the one in the noise in a score-based model. During training time, you are essentially learning a sequence of denoisers, one for every time step. And once you have the denoisers, to generate samples, what you do is you just use the decoders, just like you would do in a normal VAE. And because basically the means of these Gaussians that are defined in the decoders at optimality essentially correspond to the score functions, the updates that you do end up looking very, very similar to the ones you would do in an ELBO line-driven dynamics kind of procedure, where at every step you would essentially follow the score and you add a little bit of noise at every step because the decoders are Gaussians. And so in order to sample from a Gaussian, you would compute the mean, and then you would add a little bit of noise to that vector. And so very similar to the procedure that we would do in a line-driven dynamics, where again, you would follow the gradient and you would add a little bit of noise. And yeah, we've seen the architectures are also very similar, but kind of like where we stopped last time was to think about the diffusion version of this, which is really the case when we have an infinite number of noise levels. So instead of having, let's say, 1,000 different versions of the data density that has been perturbed with increasingly large amounts of noise, we can consider this continuum, this spectrum of distributions that are now indexed by this variable t, which you can think of it as time, that goes from 0 to factor t. And so just like before, on the one end, we have the clean data distribution. At the other end, we have a pure noise kind of distribution, but now we have a continuum. And this continuum is actually going to be useful because it exposes kind of like additional structure in the model that we can take advantage for coming up with more efficient samplers, for evaluating likelihoods exactly, and so forth. And so you can think of the variational kind of VAE perspective that we talked about so far as some kind of discretization of this continuum version of the process, where we only look at, let's say, 1,000 different slices in this sequence. But we can kind of like it makes sense to think about the continuous version because, as we'll see, yeah, it allows us to do more essentially. And so once we go in the continuous version, again, basically there is a stochastic process that describes this process of going from data to noise, where at every step you add a little bit of noise, just like in the previous case, except that we get this kind of continuous time process by thinking about what happens if you were to take increasingly small kind of like discretization steps in the previous perspective. And so before we were kind of like jumping, we were taking 1,000 different steps, adding more and more and more noise until we get to the end. You can imagine a continuous process that goes from left to right, where at every step we had an infinitesimally small amount of noise. But of course, over time, if you integrate all of this noise, you get the same effect of basically destroying the entire structure in the data. And so formally, what we're dealing with here is a stochastic process where we have a collection of random variables. And now this collection of random variables we have an infinite number of random variables. Right? Before we had, let's say, 1,000. You had a VAE with your, maybe 1,000 different layers, and so you had 1,000 different random variables, one for every discrete time step. Now we have an infinite number of random variables. There is one for every t, and t is continuous. So you can take an infinite number of values between 0 and capital T. And these random variables have densities, just like in the VAE perspective. There is a probability density function associated with each one of these random variables. And it turns out that we can describe how these random variables are related to each other through a stochastic differential equation, which you can think of it as a way that would allow you to sample values for these random variables. It would take a whole quarter to explain exactly what that notation means and what a stochastic differential equation is, but essentially, you can imagine that this is really what happens if you take the previous VAE perspective and you make the intervals, the time steps between one slice and the next one very, very small. So dxt is basically the difference between xt and xt plus delta, kind of like a neighboring slice. And the difference between these two random variables is given by some deterministic value, which is just like the drift it's called, plus a little bit of noise, an infinitesimal amount of noise. And for simplicity here, we can think about, if you think about the process of just adding noise, you can describe it with a very simple kind of like stochastic differential equation, where the difference between the value of the random variable at time t and the value of the random variable at time t plus epsilon or t plus delta t is just an infinitesimally small amount of noise, which is what this kind of like equation really means. Yeah, so the drift is basically telling you how you should change, basically. Like you can imagine that there's some kind of like velocity, like if you think about the dynamics. Like if you think about kind of like how xt evolves. So xt is, let's say, an image, and as you increase time, the value of the pixels change. And if you don't have the drift, then the change is entirely driven by noise, which is what we're doing here. As what we will see is that when we reverse the direction of time, then it becomes very important to actually take into account the drift, because we want to have some kind of like velocity field that is pushing the images towards the directions where we know there is high probability mass. And so it's going to be important to have a drift, because if you think about, if you flip the direction of time and you want to go from noise to data, it's not a purely random process. You kind of like have to change the values of the pixels in a very structured way to generate at the other end something that is indeed looking like an image. And so if you see at this end, all the probability mass is kind of like spread out according to a Gaussian. But if you want to get to something that looks like this, where all the probability mass is kind of like here and here, then you have to have some kind of like velocity that is pushing the particles, that is pushing this trajectory to go either here or here, essentially, because you want to have the right probability mass at the other end. This is a special case of this, where the drift is 0. And it turns out this kind of stochastic differential equation is the one that captures this kind of like relatively simple behavior of just adding noise to the data. Okay. More generally, you could have a drift, and we'll see that we need the drift to talk about the reverse process. But what I'm saying here is that this process of adding noise to the data, which is just like a very fine discretization of what happens in the previous VAE, can be described by this simple kind of like stochastic differential equation, where the dxt's, the difference in the value that the random variables take at a very small time increment, is just an infinitesimally small amount of noise that you add. So I guess if you add Gaussian noise at the level of the densities, you are essentially convolving. So there is an implicit convolution that is happening here. So if you think about the shape of the densities, like you have a density here, and then you get if you take one of the slices here, you get a different density, which is actually the previous density convolved with a Gaussian kernel, because that's what happens if you sum up two independent random variables. So there is an implicit convolution kind of happening here at the level of the densities. Cool. Now, the reason this is interesting is that we can think about just changing the direction of time. So we can think about the process as going from right to left in the previous slide, so going from noise to data. And so again, we have these trajectories, which are samples from the stochastic process. So these are like realizations of these random variables that are consistent with the underlying stochastic differential equation. And if you could somehow sample from this stochastic process, then you would be able to generate data by basically just discarding everything and just looking at the final endpoint of this trajectory. And the beauty is that if you essentially do a change of variables, and it's a little bit more complicated because this is stochastic, but essentially if you apply a change of variables and you swap, you replace t with capital T minus t prime, so you just literally flip the direction of the time axis, and you can obtain a new stochastic differential equation that describes exactly the reverse process. And the interesting bit is that this stochastic differential equation now has a drift term, which is this red term here, which is the score of the corresponding perturbed data density at time t. So so this is the exact reverse of this SDE. The forward SDE doesn't have the drift term. If it had the drift term, then you would have to account for it in the reverse SDE. You would have to basically flip it. But we don't have to, because this is for now. But you could include it if you wanted. This is kind of like the simplest case where I don't have the drift. If you had it, you could include it. So in the forward process, there's no drift. It's purely driven by noise. So you can think of it literally, it's kind of like a random walk. So at every step, let's say if it was a one-dimensional random walk, you can go either left or right with some probability. And then after a sufficiently large amount of time, you forget about the initial condition and you get an unknown kind of like distribution. This is kind of like the continuous time version of that, where at every step you move by a little bit, and the amount you move is basically this dW, which is kind of like the amount that you move towards the left or towards the right, essentially. But it's essentially a random walk. And it turns out that you can reverse it, and that there is a way to describe this reverse random walk, where you go from noise to data, and it can be captured exactly if you knew the score function. So they're describing exactly the same thing. So both of these SDEs describe these kind of trajectories. The only thing the only thing that has happened here is that we're changing the direction of time. So if you flip the direction of time and you kind of like, if you start from noise and you solve this SDE, you get exactly the same kind of traces that you would have gotten if you were to start from data and add noise to it in the other direction. These two are exactly equivalent to the extent that you know the score function. So in this case, you have to go towards, because this is trying to sample from the data distribution. So if the data distribution had a mixture of two Gaussians, so there's two things I can have, two possible images, let's say, and it's either one or the other, then you'd want the process to go there. What we'll see, and that's towards the end of this lecture, is that how to do controllable generation, which is the idea. If you wanted to only sample one of them, maybe one is cat and the other one is dog. And let's say that you had a classifier that tells you if you're dealing with a cat or a dog. This kind of perspective allows you to do it in a very principled way. So there is a relatively simple algebra that allows you to basically change the drift. And essentially all you have to do is you just basically apply Bayes' rule and you change the drift to also push you towards x's that are likely to be classified as, let's say you want a dog, that are likely to be classified as a dog. So just by changing there is basically a principled way to change the drift to push you in a certain direction. And that is probably the right way of basically sampling from a conditional distribution that might be defined in terms of a classifier, or the more relevant example would be text to image, where you have a distribution over images that have corresponding captions. Now you want to be able to sample images with a particular caption. Then you don't want to necessarily sample from the marginal distribution over all the images that you had in the training set, but you want to be able to sample from the condition. So we'll see that there is a way to change this reverse SDE to actually sample from not the data distribution, but some version of the data distribution that is, let's say, more skewed towards a particular caption that you want. So this is the gradient only with respect to x
at a given
t. Okay. There is actually ways to also try to estimate the score with respect to t, which is the partial derivative with respect to t. Turns out you can also estimate it with score matching kind of losses. We actually had a paper on kind of like doing these sort of things where the nice thing about that is that I guess a lot of the structure deals with it's very specific to the diffusion kind of math. And the moment that one doesn't hold anymore, like let's say if you're trying to interpolate between two different data sets, then it's no longer a diffusion. And so the math is different. And in that case, you do need the score with the gradient with respect to t also. So you can do more interesting things if you had it, but here you don't need it. It turns out that because of the Fokker-Planck equation, the gradient with respect to t is completely determined by this. In the forward SDE, there is no drift. This is just a random walk where you're essentially just adding noise to the data. So there is no particular direction. Like if you're going from data to noise, there is no particular direction that you want to kind of like bias your trajectories towards. The score is deterministic drift. Yeah. So and then there is still noise. As you said, there is also a little bit of noise at every step. In the second one, we have both deterministic drift and random noise. So it still has both. And you can think of it as kind of like if you were to discretize this SDE, you'd get essentially Langevin dynamics, or essentially the same sampling procedure of the DPM, where you would follow the gradient and add a little bit of noise at every step. You can think of that as basically just a discretization of this SDE. And then basically, then what you can do is you can build a generative model here by learning this, as usual, like if you knew these score functions, then you could just solve this SDE, generate trajectories, kind of like, wait, let me see whether I can get the animation going again. Yeah. So if you could somehow simulate this process, this SDE, or solve this SDE, then we would be able to generate samples at the end. But to do that, you need to know this red term. You need to know the score, which we know it exists, but we don't know the value of it. The only thing we have access to, as usual, is data. And so you can get a generative model by basically trying to learn these score functions using a neural network. Just like before, there is a neural network that parameterized by theta, that at every x tries to estimate the corresponding score at that x for the density corresponding to time t. So this is the same as in the DPM case. You had exactly this thing, but you only cared about, let's say, 1,000 different time indexes, which were those 1,000 different views of the original data density that you were considering in your variational autoencoder. Now, again, we have an infinite collection of score functions because t is real value here. And you can use, as usual, you can basically estimate these things using score matching. So you have the usual kind of like L2 regression loss, where you try to make sure that your estimated score at every x is close to the true score, as measured by L2 distance, on average with respect to the data distribution. And whenever you want to estimate the score of data plus noise, this is something that we can do with denoising score matching, essentially. So again, solving this training objective corresponds to learning a sequence of denoisers. And it's not a collection of 1,000 different denoisers. It's an infinite collection of denoisers, once for every t, but again, it's the usual thing. And now what you can do is, now you can plug that into that reverse time SDE. And if you discretize this SDE, which basically means that, you just discretize the time axis. And so you just look at, instead of dx, you have x t plus 1 minus xt, essentially. And you integrate that stochastic differential equation, you get, once again, some kind of update rule that is essentially the same, that is very similar to Langevin dynamics, and it's exactly the same update rule that you would use in DPM, which is at every step, follow the gradient and then add a little bit of noise, which is the same thing as Langevin dynamics, follow the score, add a little bit of noise. And but you can think of this process as basically trying to start from noise, and then you're trying to kind of like compute this red curve to get to a good approximation of a data point. We are dealing with a computer, so you cannot deal with infinite, with truly continuous time processes. So you have to discretize time. You have to discretize the time axis, and you can try to kind of like approximate this red trajectory with essentially some Taylor expansion. So this is really what this thing is just a Taylor expansion to what you should be doing. And that's what the DPM does. So the DPM basically has 1,000 different time slices, and then you would try to approximate kind of like this red curve by taking steps according to the essentially following this white arrow corresponds to sampling from one of the decoders that defines the DDPM kind of model. And because you're kind of like discretizing time, there is going to be some error that is happening. There's going to be some numerical errors that can accumulate over time. And you can think of what a score-based model, MCMC, kind of does as essentially trying to use Lagrangian dynamics to get a good sample from the density corresponding to that time. And so you can actually combine the sampling procedure of DDPM with the sampling procedure of a score-based model, and you're going to have increased compute cost, but you can get a closer approximation to the solution of this stochastic differential equation that is defined over a continuous time. One of the nice things about this whole SDE perspective, which you might wonder why are we going through all of this, is that there is a way to obtain an equivalent kind of, there is basically a way to convert the SDE to an ordinary differential equation where there is no longer noise added at every step. And so that basically corresponds to converting the VAE into a flow model. Because this is essentially kind of like an infinitely deep VAE, where there is a lot of, as you go through this trajectory, you're kind of like sampling from a lot of different decoders, right? And a VAE is, the decoders are stochastic, so you would always add a little bit of noise at every step. If you think about a flow model, that would be deterministic. So there is randomness in the prior, which is basically the initial condition of this process, but then the dynamics are completely deterministic. All the transformations are deterministic. And that will see that it's also possible to do it because we have the continuous time kind of formulation. Is if you don't use it, then you have a score-based model. So if you just don't use the predictor, you just use corrector, then you have a score-based model. If you just use predictor, then you have a DDPM. If you use both, you get something a little bit more expensive that actually gives you better samples because it's a closer approximation to the basically underlying red curve, which is what you would really want, essentially. Recall that basically the ELBO objective is trying to essentially invert the decoder is trying to invert the encoder. And the decoder is forced to be Gaussian, just by definition. And basically, the true denoising process is not necessarily Gaussian. The one that you would get if you were to really invert the denoising process. And so no matter how clever you are in selecting the mean and the variance of your Gaussian decoder, there might always be a gap between, if you think about the ELBO, between the encoder and the inverse of the decoder. And so you might not be, which means that the ELBO is not tight and means that you're not modeling the data distribution perfectly. And the only, basically what, another way to think about this math is that only in the limit of continuous time, or basically an infinitely large number of steps, it's possible to essentially get a tight ELBO where if the forward process is Gaussian, the reverse process is also Gaussian. And so you're not losing anything, but basically assuming that the decoders are Gaussian. But that's only true if you really have an infinite number of steps. So it's only true in continuous time. So the predictor would just take one step. The corrector is just using Lagrangian to try to generate a sample from the density corresponding to that. So no, you would still do, let's say, 1,000 different steps, but not an infinite number. Like in this case, I guess I'm showing 3 steps. In reality, you would have 1,000 of these different wide arrows. Cool. So the interesting thing is that so far we've been talking about stochastic differential equations where we have these paths that you can think either in forward or reverse, going from data to noise or noise to data. It turns out that it's possible to define a process where the dynamics are entirely deterministic. And it's equivalent in the sense that the densities that you get at every time step are the same as the one you would get by solving the stochastic differential equation either in forward or reverse time. So we basically have two different stochastic processes. One is basically you have a stochastic initial condition and then deterministic dynamics. Those are those white kind of trajectories that you see. And another one where there is stochasticity at the beginning and then also at every step. And the processes are the same in the sense that for every slice that you want to take, so for every time index, the marginal distributions are the same. So if you look at, how frequently you see a white arrow, a white line versus one of the colored lines passing through a point, you would get exactly the same kind of density, including at time 0, which is the one that we care about, which is the one corresponding to data, basically. And so what this means is that we can basically define a process that is entirely deterministic. And as we were saying before, this essentially corresponds to converting a VAE into a flow model. So in a VAE, you would have this process where at every step, you can sample from a decoder, which has stochasticity. In a flow model, you would have all these layers that are just transforming the data through some invertible kind of transformation. And this is essentially what's going on here. What we're doing is we're converting the model into an infinitely deep flow model, a continuous time normalizing flow model, where there is an infinite sequence of invertible transformations, which basically correspond to the dynamics of this defined by this ordinary differential equation. So the difference here is that if you look at this equation, this is no longer a stochastic differential equation. There is no noise added at every step. Now, we only have a drift term here, and there is absolutely no noise added during the sampling process. And again, you can see that the only thing that you need in order to be able to define this ordinary differential equation is the score function. So if you have the score function or this sequence of score functions, one for every time step, then you can equivalently generate data from your data distribution by solving an ordinary differential equation. So you just initialize this trajectory. You basically, once again, flip the direction of time. You sample an initial condition by sampling from the prior, which is this usual pure noise kind of distribution, and then you follow one of these white trajectories, and at the end you get a data point, which is exactly the kind of thing you would do in a flow model, where you sample from the prior, and then you transform it using a deterministic invertible transformation to get a data point. And so that's basically what you would do. We have this process, and we can think of this basically as a continuous time normalizing flow. And the reason this is, this is indeed, or intuitively, the reason you can think of this as a normalizing flow is because these ordinary differential equations have a unique solution. So basically these white trajectories, they cannot cross each other, they cannot overlap. Which means that there is some kind of mapping, which is invertible, that goes from here to here, and which is the mapping defined by the solution of the ordinary differential equation, which up to some technical condition exists and is unique. And so, we can think of this as a very kind of flexible kind of flow model, where the invertible mapping is defined by the dynamics of a ordinary differential equation, where the dynamics are defined by a neural network. So it's a neural ODE, if you've seen these kind of models a neural ordinary differential equation. So it's a deep learning model where the computation is defined by what you get by solving an ordinary differential equation, where the dynamics are defined by a neural network, which in this case is the score function. The ODE is equivalent to the SDE, so they define exactly the same kind of distribution at every step. So the distribution that you get at this end, so a capital T, is exactly the same that you would have gotten if you were to just add, kind of doing your random walk where you add the noise at every step. This is true if you have the exact score function at every step, which is never the case in practice. But to the extent that you have the exact score function, the mapping between the SDE and the ODE is exact. So they're exactly defining the same. It's a different stochastic process with exactly the same marginal distributions. Another way to think about it is that you're essentially reparameterizing the randomness. So remember that when we were sampling, we were thinking about variational inference and how to backprop through basically the encoder, which is like the stochastic kind of computation. We were showing that it's possible to sample from a Gaussian by basically transforming some simple noise through a deterministic kind of transformation. And in some sense, what's happening here is that we are reparameterizing. There is a computation graph where we add randomness at every step. And we're defining a somewhat equivalent computation graph where we're putting all the randomness in the initial condition. And then we're transforming it deterministically. But yeah, the key thing here is that the mapping is invertible, because if you think about an ordinary differential equation, there is a deterministic dynamic. So whenever you are somewhere, the ordinary differential equation will push you somewhere in the next kind of location based on the dynamics, and it cannot bifurcate. There is only one next state that you get by solving the ODE, and so there is no way for two things to possibly cross. And we can invert it by basically going backwards from capital T to 0, which is from noise to data. And this is important for several reasons. The main one is that we can now think, if you think of this process of going from some simple prior, a Gaussian distribution, to data through an invertible mapping, this is once again a normalizing flow. And so what you can do is you can actually compute the likelihood of any data point, of any X, of any image, by using essentially the change of variable formula. Like as in a regular flow model, if you want to evaluate the likelihood of some X under the flow model, what you would do is you would invert the flow to go in the prior space, which in this case corresponds to solving the ODE backwards and find the corresponding point in the latent space, evaluating the likelihood of that point under the prior, and the prior is known, is fixed, so we can do it efficiently. Then, as usual, you have to keep track of the change of variable formula, essentially. So you have to keep track of how much the volume is squeezed or expanded as you transform a data point through this ordinary differential equation. We're integrating it. So it looks like this. So you have to integrate so it's an ordinary differential equation. So you can imagine if you were to discretize it, the score will give you the direction that you should move by a little bit, and then you need to recompute it. So you still need to somehow solve an ordinary differential equation on a computer, which involves discretizations. But what you get is that people have spent 50 years or more developing really good methods for solving ordinary differential equations very efficiently. Like there is very clever schemes for choosing the step size, very clever schemes for kind of reducing the kind of numerical errors that you get as you go from left to right. And all that machinery can be used and has been used to basically accelerate sampling, generate higher quality samples. And that's one of the main reasons this perspective is so powerful, because once you reduce sampling to solve an ODE, you suddenly have access to a lot of really smart techniques that people have developed to come up with good numerical approximations to the ordinary differential equation. If you recall, you can think of the DPM as a VAE with a fixed encoder, which happens to also have the same dimension, and that's very important for getting the method to work in practice. We'll talk about latent diffusion models in a few slides, and that basically, embraces more like the VAE perspective of saying, well, let's have a first kind of encoder and decoder that will map the data to a lower dimensional space, and then learn a diffusion model over that latent space. And so you get kind of like the best of both worlds, where you've both reduced the dimensionality and you can still use this machinery that we know in practice works very well. The Fokker-Planck equation is basically telling you how the densities change. It's a partial differential equation that relates the partial derivative of PT, basically, of the PTX, so the probability of X, across as you change T, to spatial derivatives, which essentially the trace of the Jacobian. And so that's why the things work out. And that's actually how you do the conversion from the SDE to the ODE. You just basically work through the Fokker-Planck equation. Like everything is relying on this diffusion, kind of underlying diffusion structure. But basically, what I'm saying here is that you can use something that is very similar to the vanilla change of variable formula that we were using in flow models to actually compute exact likelihoods using these models. And again, basically, if you want to evaluate the probability of a data point x0, what you would do is you would solve the ODE backwards. So you would go from data to noise to get xt. You would evaluate the probability of that latent variable under the prior, and that's this piece. And then you have to look at the basically how the volume is changed along the trajectory, and it's no longer the determinant of the Jacobian that you have to look at. It turns out that what you have to do is you have to integrate the trace of the Jacobian, which is something that you can actually evaluate pretty efficiently. So that's basically what a consistency model does. There is this recent model that was developed by Yang actually at OpenAI, and essentially what they do is they try to learn a neural network that directly outputs the solution of the ODE in one step. And because there is an underlying ODE, there is some clever kind of like objectives that you can use for training the neural network. But yeah, that's kind of like, as we'll see, there is, once you take this perspective, you can distill down, then you can get very fast kind of like sampling procedures by taking advantage of this underlying ODE perspective. You're just trying to solve ODEs, and there is a lot of tricks that you can use to get very fast solvers. But yeah, one nice thing you get is you can compute likelihoods. So you can convert the VAE into a flow model, and then you can compute likelihoods. So the good thing is that once you kind of like learn the score once, and then it's opening up, there's many different ways of kind of like using the score at inference time to generate samples. And ODEs are good to generate samples very efficiently. The SDE is still valuable, and in some cases it can actually generate higher quality samples. And the reason is that if you think about what happens when you solve the ODE, you have kind of like, you start with pure noise, and then you follow this denoiser essentially to try to approximate one of these trajectories. But then, let's say that the denoiser is not perfect and you're making some small mistakes, then the kind of images that you see around the middle of this trajectory, they're supposed to look like data plus noise, but they're not quite going to be data plus noise because your score function is not perfect. And so then you're starting to feed data that is a little bit different from the ones you've seen during training in your denoiser, which is your score model. And so you're going to have compounding errors because the images that you're feeding into your denoiser, which is basically what you get by following these trajectories, are not quite going to be exactly the ones that you've used for training the model, which is what you get by actually going from data to data plus noise, by really just adding noise to the data. And so if you think about the SDE, on the other hand, you're actually adding noise at every step. And that's good because you're making the inputs to the denoiser look more like the ones you've seen during training. The problem is that solving SDEs efficiently is a lot harder. And so if you want fast sampling, the ODE perspective is much more convenient to work with. Yep, so we can get likelihoods, and what you have to do is to basically solve an ODE where you kind of like solve this integral over time by, you can literally call a black box ODE solver and kind of compute this quantity. And it turns out that it's very competitive. So even though these models are not trained by maximum likelihood, so they are not trained as a flow model. And the reason they are not trained as a flow model, because you could, in principle, you could try to optimize, you could do exact maximum likelihood, right? Because you could try to evaluate this expression over your data set and optimize it as a function of theta. But it's numerically very tricky and very, very expensive because you have to differentiate through an ODE solver. Because you'd have to optimize the parameters theta such that the result of the ODE solver gives you high likelihood, which is extremely difficult to do in practice. So you don't train the model at maximum likelihood, you still train it by score matching, but still you get very good likelihoods. Like you can actually, this is achieving state-of-the-art results on image data sets because, yeah, unclear why, but I mean, well, we know sort of why, because there is, as we've seen, kind of like score matching has an ELBO interpretation, so it's not too surprising that by solving by matching gradients, by doing score matching, you're kind of like optimizing an ELBO and evidence lower bound, so it's not too surprising that the likelihoods are good too. But yeah, the results are very, very good in terms of likelihoods. The other thing that you can do is you can get accelerated samples. Specifically, DDIM is very often used as a sampling strategy where instead of having to go through, let's say, 1,000 different denoising steps, which is what you would do if you had a DDPM kind of model, essentially what you can do is you can coarsely discretize the time axis. Let's say you only look at 30 different steps instead of 1,000, and then you take big steps, essentially. You take big jumps. And you're going to pay a price because there's going to be more numerical errors, but it's much faster. And in practice, this is what people use. And there is a little bit more, you can be a little bit more clever than this because there is some special structure, like a piece of the ODE is linear, so you can actually solve it in closed form. But essentially, this is how you get fast sampling. You just coarsely discretize the time axis and you take big steps. So you can generate an image. Instead of doing 1,000 steps, you maybe only need to do 30 steps. And that becomes a parameter that you can use to decide how much compute you wanna use, how much effort you wanna put in at inference time. The more steps you take, the more accurate the solution to the ODE becomes. But of course, the more expensive it actually is. Just to clarify, there is not a score function for the ODE and one for the SDE. There is just a single score function, which is the score function of the data density plus noise. And so it's the same whether you take the ODE perspective or the SDE perspective. The marginals that you get with the two perspectives are the same. And so the scores are the same. And they are always learned by score matching. Then at the inference time, you can do different things. At the inference time, you can solve the SDE, you can solve the ODE, but the scores are the same. This is one way to get very fast sampling, and there is a lot of better now. I mean, there is a lot of other kind of like clever ways of solving ordinary differential equations, Hune kind of solvers, like where you take half steps. There is a lot of clever ideas that people have developed for numerically solving ordinary differential equation pretty accurately with relatively small amounts of compute. And yeah, this can give you very high, very, very big speed ups with comparable sample quality. Another fun thing you can do is you can actually use parallel. This is actually a recent paper that we have on using these fancy ODE solvers, which are basically parallel in time, where instead of trying to compute the trajectory of the solution of the ODE one step at a time, which is what the DPM would do, you kind of like try to guess the whole trajectory by leveraging many, many GPUs. And so instead of trying to go one step at a time, trying to find a good approximation to the true underlying trajectories, you use multiple GPUs to kind of denoise the whole, a bunch of images basically, a batch of images in parallel. And so if you're willing to trade more compute for speed, you can actually get exactly the same solution that you would have gotten if you were to go through individual steps using a lot more parallel compute, but in a vastly smaller kind of like amount of wall clock time. So this, okay, I'm not going to go into too much detail, but basically there are tricks for using, again, advanced ODE solvers to further speed up the sampling process. And let's see whether I can get that. Basically, what you're doing is, instead of going, the DPM would go one step at a time, trying to compute the trajectory, which is the brown kind of dot that you see moves slowly. What we're doing is we're using multiple GPUs to compute a whole piece of the trajectory in parallel. So it's a way to basically trade off compute for reduced wall clock time. Another thing you can do is distillation. The basic idea is that you can think of DDIM as a teacher model. So you have a DDIM model that would compute, let's say, the solution of the ODE based on some kind of discretization of the time axis. And then what you do is you train a student model that basically does in one step what DDIM would do in two steps. So DDIM maybe would take two steps to go from here to here and then from here to here. And you can train a separate student model, which is another score-based model that is trying to skip and doing, basically, it's trying to define a new score function such that if you were to take one step, according to that score function, you would get the same result as what you would have gotten if you were to take two steps of the original score function under DDIM. So again, it's kind of like trying to distill the solution of the ODE according to a different, or find a different kind of ODE that would give you the same sort of solution, but in using less steps. And then what you do is you recursively apply this. So then you use this new student model as the teacher, and you get another student that tries to do in one step what the other thing does in two steps, which becomes 4 steps of the original model. And you keep doing this until you can distill down to a very small number of steps. So these are some of the results, not quite one map, but these are some of a recent paper we have on this progressive distillation. This is on text-to-image models. This is with the stability AI people stable diffusion, where you can actually, let's say, you can see here images generated in just 2 steps or 4 steps or 8 steps by distilling a model that originally had was say 1,000 steps, and essentially using this trick of reducing in half and half and half until you get down to 2, 4, or 8 steps. And you can see the quality is pretty good in terms of the sample quality. And this is, of course, much more efficient. It's also tempting to get at the idea of generating in one step. Consistency models directly try to do it in just one step. And so they directly try to learn a mapping from the kind of like what you would get at the end of this progressive distillation. And they do it with a different loss. So there is no progressive distillation. They just do it in one shot, essentially. But they're trying to get at a very similar kind of result. Cool. And so, yeah, distillation is a good way to achieve fast sampling. There's also this thing called consistency models that is essentially, I think you might have seen stability. I recently released a model yesterday, I think, on real time that allows you to do real-time generation, and it's something like this, some version of scored distillation plus some GAN that they throw in, but it's kind of like a combination of this thing plus a GAN, and they were apparently able to get a model that is so fast that it's basically real time. So you type, it's a text-to-image model where you can type what you want and it generates images in real time. Doing a combination of this and GANs. Speaking of stable diffusion and stability AI, the key difference between what they do and what we've been talking so far is that they use a latent diffusion model. And essentially, what they do is they add an extra. You think of a diffusion model as a VAE. What they do is they add another encoder and decoder layer at the beginning. And the purpose of this encoder and decoder is to reduce the dimensionality of the data. So that instead of having to do diffusion model over pixels, you train a diffusion model over the latent space of a autoencoder or variational autoencoder. But literally, you can think of what's happening as just an extra. If you think of the hierarchical VAE, you just add an extra encoder and an extra decoder at the very end of the stack. So those distilled models were actually distilled latent diffusion models. So the reason you might want to do this is that it's a lot faster to train models, let's say on low resolution kind of images or low dimensional data in terms of the kind of memory that you need for training a diffusion model. So it's actually much faster to train a diffusion model if you could somehow train it, not on the original pixel space, but you can do it over some sort of low dimensional representation space. And the other advantage of this, if you take this perspective, is that now you can suddenly use diffusion models for essentially any data modality, including text. So some of the diffusion models that people have tried on text essentially take this perspective. So you start with discrete inputs X, and then you encode them into a continuous latent space, and then you decode them back with the decoder, and then you train the diffusion model over the latent space, which is now continuous, and so the math works out. And of course, this only works to the extent that the original encoder and decoder does a pretty good job at basically reconstructing the data. Yeah, what stable diffusion does, they actually pre-train the autoencoder. So it's not trained end-to-end, even though you could, because it's just a VAE, so you could actually train the whole thing end-to-end. What they do is they pre-train the autoencoder, and they really just care about getting good reconstruction. So they don't care too much about the distribution of the latent space to be similar to a Gaussian. They just care about getting a good autoencoder, essentially. And then in a separate stage, they keep the initial autoencoder fixed, and they just train the diffusion model over the latent space. And that works really well. And these were some of the, they got a lot of success with this approach. They were one of the first to train a large-scale model on a lot of, on Lion, like large-scale image data sets, and it's been widely adopted by a lot of the community. People have actually been successful even in training diffusion models in pixel space, but the most successful versions are usually either on the latent space or downscaled versions of the images. So they have kind of like this encoder and decoder is more like a downscaling and an upscaling. But essentially the trick is be able to train a model over a low resolution kind of data. And literally what you do is you can encode all your data set, then pretend that the data is whatever comes out from the original encoder and train your diffusion model over whatever you get. So they regularize it to be close to a Gaussian, if I remember correctly, but it's a very weak kind of regularization. Really all they care about is reconstruction. So if you think about the ELBO as reconstruction plus matching the prior, they don't care too much about matching the prior because they are not really going to sample from essentially they use the diffusion model as the prior, and the diffusion model can generate anything. It's a very powerful kind of prior distribution. So you don't have to regularize the VAE to have a distribution over latents that is close to Gaussian, because anyways, then you're going to fit a VAE to whatever comes out from the original. You're going to fit a diffusion model to whatever comes out from the encoder of this initial VAE, and so it's not really necessary to regularize. So maybe there's kind of like two priors. So if you just think about the basic VAE that goes from high dimensional to low dimensional data, you could have a prior there when you pre-train this model. But since you're not really going to use that model to sample from, you don't really care about matching the prior. In the diffusion model, the prior at this end is the usual Gaussian. So the diffusion model that you learn over the latent space of the initial autoencoder has a Gaussian prior. How do you get text into one of these models? And there's several ways to do it. So let's say that you have a data set that is not just images X, but it's images and captions, where I'm denoting with the caption with Y here, because it could also be a class label, let's say. So really, what you're trying to do is you're trying not to learn the joint distribution over X comma Y, because you don't care about generating images and the corresponding captions. You just care about learning the conditional distribution of an image X given the corresponding label or given the corresponding caption Y. Essentially, if you want to use a diffusion model for this, or a score-based model, this boils down to learning a score function for this conditional distribution of X given Y. And so now the score function, or the denoiser, as usual, needs to take as input xt, which is a noisy image. It needs to take as input t, which is the time variable in the diffusion process, or the sigma level, the amount of noise that you're adding to the image. And now, basically, the denoiser or the score function gets this side information y as an extra input. So the denoiser knows what is the caption of the image, and it's allowed to take advantage of that information while it's trying to guess the noise level or equivalently denoise the image. And so in some sense, you can think of it as a slightly easier problem because the denoiser has access to the class label y or the caption y while it's trying to denoise images, essentially. And so then it becomes a matter of cooking up a suitable architecture where you're feeding into the unit, you're feeding in t, you're feeding in the image xt, and then you need to feed in y, which is, let's say, a caption into the architecture. And the way to do it would be, for example, you have some pre-trained language model that somehow can take text and map it to a vector representation of the meaning of the caption, and then you kind of incorporate it in the neural network, and there's different ways of doing it, but maybe doing some kind of cross-attention. There's different architectures, but essentially you want to add the caption y as an additional input to your neural network architecture. This is the most kind of like vanilla way of doing things, which is you just train a conditional model, essentially. Now, the more interesting thing, I think, is when you want to control the generation process, but you don't want to train a different model. So the idea is that you might have trained a generative model over images, and let's say there's two types of images, dogs and cats. And then let's say that now we only want to generate, back to the question I was asked initially during the class, is what if you want to generate image only of dogs? So if you have some kind of classifier, P of y given x, that can tell you whether an image x corresponds to the label dog or not, how do we generate an image x that would be labeled as a dog, with a label y equals dog? Mathematically, what we want to do is we want to combine this prior distribution, P of x, with this likelihood, P of y given x, which let's say is given by a classifier. And what we want to do is we want to sample from the posterior distribution, x given y. So we know that we want a dog, and we want to sample from the conditional distribution of x, given that the label is dog. And if you recall, this conditional distribution of x given y is completely determined by P of x and P of y given x through Bayes' rule. Right? This inverse distribution is obtained by that equation that you see there, which is just Bayes' rule. So if you want to get P of x given y, you multiply the prior with the likelihood, and then you normalize to get a valid distribution. And when, as the denominator here is in principle something you can obtain by integrating the numerator over x, right? So what you have in the numerator is P of x comma y, and in the denominator you have P of y, which is what you would get if you integrate over all possible x's, P of x comma y. So everything is completely determined in terms of the prior and this classifier. So in theory, if you have a pre-trained kind of, let's say, generative model over images, and somebody gives you a classifier, you have all the information that you need to define this conditional distribution of x given y. It's just a matter of computing that expression using Bayes' rule. And unfortunately, even though in theory you have access to the prior, you have access to the likelihood, computing the denominator is the usual hard part. It's the same problem as computing normalization constants in energy-based models, basically. It requires an integral over x, and you cannot really compute it. And so in practice, even though everything is well defined and you have all the information that you would need, it's not tractable. But if you work at the level of scores, so if you take the gradients of the log of that expression, you get that the score of the inverse distribution is given by the score of the prior, the score of the likelihood, and then we have this term, which is the score of the normalization constant. And just like in energy-based models, remember that that term goes to 0 because it does not depend on x. And so basically, if you're working at the level of scores, there is very simple algebra that you need to do to get the score of the posterior is you just sum up the score of the prior and the score of the likelihood. And what this means is that basically, when you think about that SDE or the ODE, all you have to do is you have to just replace the score of the prior with the score of the posterior. And really all you have to do is, if you know the score of the prior, you have a pre-trained model, and let's say you have a classifier that is able to tell you what is the label y for a given x, as long as you can take gradients of that object with respect to x, which is basically if you have a, let's say, an image classifier, you just need to be able to take gradients of the classifier with respect to the inputs. then you can just sum them up and you have the exact score of the posterior. So if basically you do Langevin dynamics, or you solve the SDE or the ODE, and instead of following the gradient of the likelihood of the prior, you follow the gradient of the likelihood of the prior plus the likelihood, you do the right thing. And so intuitively, if you think about Langevin dynamics, what you're doing is you're trying to follow the direction that increases the likelihood of the image with respect to the prior. But at the same time, you're trying to make sure that the classifier will predict that image as belonging to the class dog. And so you're just changing the drift in the ODE to push the samples towards the ones that will be classified as a dog. In reality, you would need to have this classifier with respect to XT, which is like a noisy version of the image. But yeah, roughly. And if you had a latent variable model, then yeah, it's a little bit more complicated because you also have to go through the original encoder and decoder. But if you're working on pixel space, this can be used. And we've used it for a number of things, like you can use it to do editing. If you want to go from strokes to images, basically it's possible to define a forward model in closed form, and you can follow it, and you can do image synthesis, or if Y is a caption, and then you have some kind of image captioning network, you can kind of steer a generative model towards one that is producing images that are consistent, that would be captioned in a particular way, and you can use it to do conditional generation, you can do text generation, and so forth. You can actually also do medical imaging problems where the likelihood is specified by how the machine works, like the MRI machine works, and Y is kind of like a measurement that you get from the machine, and then you can try to create a medical image that is likely under the prior and is consistent with a particular measurement that you get from the machine. So a lot of interesting problems can be solved this way, and even classifier-free guidance is basically based on this kind of idea. And I guess we don't have time to go through it, but it's essentially a trick to essentially get the classifier as the difference of two diffusion models, but roughly the same thing. In practice, you can either approximate it just with a classifier that works on clean data by kind of like using the denoiser to go from noisy to clean and then use the classifier. Or in some cases, it can be done in closed form, or you can do this trick where you basically train two diffusion models, one that is conditional on some side information, one that is not, and then you can get the classifier implicitly by taking the difference of the two, which is what classifier-free guidance does, which is widely used in state-of-the-art models. But essentially, they avoid training the classifier by taking the difference of two diffusion models. So they train one, let's say that is the P of X given Y, which would be just a diffusion model that takes a caption Y as an input. Then they have another model that is essentially not looking at the captions. And then during sampling, you kind of like push the model to go in the direction of the images that are consistent with the given caption and away from the ones that are from the typical image under the prior. And that's kind of like the trick that they use to generate really good quality images.